Topic 18 of our Physics 30 and 16 pages here, electricity and magnetism. Topics 18 and then 19 through whatever it is. We started off back in late February on electricity, and we introduced it, talked about a few simple, relatively simple topics when we dealt with electricity, when we first started off with electricity as well. Topics that you see up here under topic, subtopics that you see here under topic 18. We talked about charge, of course, positive charge, negative charge, and neutral charge. We remember that when we talk about all three of those charges, we're not talking about just protons and neutrons. We're talking about more of one than the other. Positive comes from having more positive than negative. Negative comes from having more negatives, more electrons than protons. And neutral comes from having an equal number of protons and neutrons. This is the one that I want to focus on here, though, right now, the charge movement. If something's going to move, what is it that's going to move? We got three things, right? We got protons, neutrons, which I'll tell you right now, that's not the answer, because that's those aren't relevant to us in electricity. We got protons, neutrons, and electrons. If something's going to move, what is it that's going to move? Electrons. And why is it electrons that are going to move as opposed to protons that are going to move? Where are they, right? If we look at the model of the atom, we've got protons and neutrons stuck in the middle here in this thing that we call the nucleus, and they're held in place. We learned later on this year, we learned that they're held in place by this force that we call the strong nuclear force. And that's a pretty strong force, and that keeps them bound together pretty well. The protons can do something. We can change the nucleus itself into something else, but then that's a nuclear process, and that's a lot harder to do. It takes a lot more energy than an electrical process, which involves electrons leaving. These electrons are orbiting around, and they're held in place by an attractive electrostatic force, but it's not nearly as strong. So it's a lot easier to get these electrons to leave the atom than it is the protons. Therefore, it's a lot easier to get electrons moving than it is to get protons moving. Again, if we're talking about protons moving, then we're dealing with a nuclear reaction, not an electrical interaction. The three laws of electric charge. There's two, what I call fundamental laws, and then there's that third one that's a result of something else that we'll talk about in just a few minutes here. First one, doesn't really matter what order we give them in here. Like charges repel. Good. Like charges repel. So if you got positive and positive, they repel each other. Negative and negative, they repel each other. Now, when are you going to see this in a question? Probably not a question that says, oh, the following is a law of the electric charge. It's probably more like some bigger context where it's a small piece of the puzzle. Always keep in mind that like charges repel each other, okay? Even if that's not the thrust of the question, okay, even if that's buried somewhere in the question, keep in mind that like charges will always repel each other, as opposed to unlike charges that attract each other. Again, a positive attracts negative, negative attracts positive. It's not likely to be the question that stands on itself, stands alone on the laws of electric charge, but it's rather going to be part of a bigger question probably, somewhere buried, just one small part of that bigger question. This is one that could more or less be its own question. This third one that says charged objects attract neutral objects. Now this word objects right here is really important. You're going to see why in a few minutes, why it's really important. Bottom line is charged objects don't attract neutral. Charged objects attract neutral objects. Protons don't attract neutrons. Positive objects attract neutral objects. I'll tell you briefly why that's the case right now, and then in just a few minutes when we talk about topic 19, charging objects, you'll see in more detail why you have to have a neutral object as opposed to just a neutral charge like a neutron. It boils down to this. Okay, if you can't get a separation of charge, I don't know if you guys remember what a separation of charge is or not, but if you can't get a separation of charge, then you can't get a neutral thing being attracted to anything. Okay, you got to have a separation of charge, and you got to have a neutral object to get a separation of charge. Okay, we'll talk about that in a little bit more detail when we get down here to topic number 19. Conductor versus an insulator. Give me an example of a conductor. Quick, give me an example of a conductor, yeah? Copper. Copper's a great example of a conductor. Silver, another one. Gold, another one. What do those have in common? Conductors tend to be metals, right? And non-conductors or insulators tend to be non-metals, plastic, glass, wood. What's the difference? Conductors are materials in which the outermost electrons are free to move. Okay? That's what electrical conduction is electrons moving from one place to the other. So a conductor is a material that allows that to happen fairly easily. We're not saying that insulators don't conduct. Okay? Everything to some level will conduct, but insulators don't conduct nearly as well. Okay? They're much poorer conductors than what we would consider a conductor to be. Now, concentration of charge, this comes down also kind of to topic 19 as well when we charge objects here. And this is where we introduced it though, concentration of charge and balancing charges. What this boils down to is, look, you touch two objects together, one is -5, the other is +5, they're going to balance out to be 0 and 0 coulombs. Maybe you touch two objects together that are +3 coulombs and +5 coulombs, they're going to balance out to be +4 coulombs and +4 coulombs. How to figure out what that value is? Is your hand up? No? How do I figure out what that value is? Yep. Add them up, divide by 2. Now, what you sometimes see is not just two charges touching each other, but three charges, usually not at once. If all three charges touch each other at once, then you would jot them, add them up, and divide by 3. Usually you don't see that. What you're more likely to see is you got three charges, charge 1, charge 2, and charge 3. Maybe you've got a kind of a step-by-step process here where charge 1 touches charge 2, it becomes 4 and 4. The other one remains 7. And then maybe charge 2 touches charge 3, where it becomes plus 5.5 and 5.5, and charge 1 remains 4. So just do it in steps. Hey, if charge 1 touches charge 2, then figure out what they become. And then if charge 2 touches charge 3, then figure out what they become. Now, sometimes what we follow this up with is a Coulomb's law problem, which we'll talk about a little bit later on as well. Basically, if charges touch each other and then you want to find a force between those charges, then you're going to have to do this, and then you're going to have to do that, the whole Coulomb's law thing. So be aware of that, not just with this topic, but with anything else that we do this year. If something happens and then something else happens, then treat it like two separate problems. Okay? If we touch charges together and then we want to find the force, then balance the charges and then use Coulomb's law to find the force. Does that make sense? Just a couple little things here. Number of electrons. We see this, I wouldn't say often, but we see this from time to time. We've seen it more than once this year, right? You want to find a number of anything. Remember the analogy that I gave you in class was the number of oranges, the number of oranges in a bag. Okay, if we have an orange that weighs 100 grams and we have a bag of oranges that weighs 600 grams, how many oranges in the bag? Okay, think about what I just said. One orange weighs 100 grams. We have a bag of oranges that weighs 600 grams. How many oranges in the bag? 6, right? All we did is took the total mass and divided it by the mass of one orange, right? That's what we do here, except it's not mass, it's charge. We take the total charge, divide it by the charge of one electron, which is 1.6 times 10 to the minus 19 coulombs. Sometimes you got to find the total charge. Sometimes you're given the total charge. Divide it by the charge of one electron. Whenever you want to find a number of anything, it's total something, charge, mass, energy, momentum, whatever, divided by the charge, mass, energy, momentum, whatever, of 1. So in this case, it's total charge divided by the charge of one electron. And finally, topic number 18, we talked about ion notation. What I mean by that is just not so much a physics concept, but just a notation that you have to be aware of just in case you see it so that you can use the physics concept. If I say Na plus, what does that mean? If I say Cl minus, what does that mean? If I say magnesium 2 plus, what does that mean? Well, Na plus means the charge of this is 1 times the elementary charge. This Cl minus is -1 times the elementary charge, and 2 plus would be 2 times the elementary charge, or 3.2 times 10 to the minus 19 coulombs. So you got the charge now, then you do something with the charge. Maybe it's an electric force question or a magnetic force question or something else entirely. The other term that I want to mention here along with this, I've only seen this a handful of times over the years, but the term singly ionized or singly charged. It doesn't look like it's spelled right, but you get what I mean. Okay, singly charged or singly ionized or doubly charged, double charged. I don't want to write that down because it's going to look even worse. If it's singly charged or singly ionized or double ionized, then it means it has a charge of 1.6 or 3.2 times 10 to the minus 19 or whatever, right? Singly would be like Na plus. Doubly would be like magnesium 2 plus. All right? Again, you're not going to get a question that says, well, what does that mean? You're going to get a question that might have that in it that you have to use as a tiny little part of a bigger picture question. All right, now we're going to get into some real stuff here. Talk about charging objects here. Conduction, induction, grounding, and so on. And this is going to lead us to this whole third law of the electric charge. It's the charged objects attract neutral objects. We got two kinds of charging here. Conduction and induction. Conduction always involves what? Think back and try to remember as much as you can remember. Right? I can tell you all this, and that's great. If you don't remember it, that's fine. I'll tell you this and hopefully refresh your memory. But the more you work to remember, the better off you're going to be here, right? Conduction doesn't always involve touching, actually. Conduction usually involves touching. Induction never involves touching. Conduction always involves, good. Conduction always involves a transfer. So that's the final criterion to determine whether it's conduction or induction. Is there a transfer of charge taking place? And induction doesn't involve a transfer of charge taking place. This can look, this can take the appearance of form of a whole different number of forms here. But in the end, conduction will always boil down to one of two things. Conduction will always boil down to two things touching each other. We got a charge of +3. We got a charge of -3. They touch each other. They balance out. Really, we already did this when we talked about conservation of charge. Okay, we call that charging by contact, or sometimes we just call it charging by conduction. And the other way we do it is by rubbing two things together, charging by friction. So here they balance. Here they don't balance. Maybe they're already balanced. If we start off with 0 and 0 and we rub them together, maybe one becomes -3, the other one becomes +3. The law of conservation of charge still dictates what happens, but it's kind of working in reverse, right? Instead of -3 and +3 becoming 0, 0 and 0 become -3 and +3. The total charge has to remain the same. Notice at the top of this page, I said for electricity intro here, possible physics principles. Okay, we talked about those physics principles in class on Tuesday or Wednesday, whatever day it was. Okay, they're listed in the bottom left-hand corner of your data sheet. If you happen to get a question in here, it's almost certainly going to be topic number 7, or principle number 7, conservation of charge. All right, so we've got charging by conduction. Charging by induction is the harder one. Charging by induction involves not transferring charge from the object doing the charging. So we've got maybe something like this that's at neutral. You get the same number of positives as negatives. We've got a negative object coming in nearby. Now remember that this negative object doesn't have to be a rod. It can be a negatively charged cloud. It can be a negatively charged anything, right? Anything that's negatively charged near a neutral anything. We had a question, I think in the multiple choice review questions that I give you in your worksheet booklet, where we had a cloud that was charged negative and the ground that was charged neutral. It's the same thing. This is your cloud, this is your ground. Question's probably not going to look like what you see up here. I have no idea what it's going to look like. Okay, but it's going to boil down to something's negative, something's neutral. What happens? Well, the positives stay where they are. And the negatives, because they're repelled by this negatively charged rod or cloud or whatever it is, they're going to go over to the left-hand side here. Not all of them. Okay, they're not all going to go over there. We draw it that way. But the reality is you don't have 3 positives and 3 negatives. You got billions of positives and negatives. You get a majority of them going to the left side, which leaves us with one side being negative and one side being positive. Now look at what happens. The side that's closest to the charging object here, so this side that's closest to the charging object right here is opposite to it. This is positive, this is negative. What happens to positives and negatives? They attract. So this neutral object, and it's still neutral with a separation of charge, this neutral object is attracted to the negative object because, ultimately, because opposites attract. And the side that's closest is opposite. Charged objects attract neutral objects. If I brought that charged object nearby a neutron, it wouldn't attract it. It wouldn't attract it because you can't get a separation of charge in the neutron. You can't get electrons being pushed away in the neutron because there are no electrons there, right? Charged objects attract neutral objects. Here's the other one. This time we got a negatively charged object. Or sorry, a neutral object. This time we're going to bring a positively charged object nearby. What happens to the protons? Nothing. What happens to the electrons? Well, this time they're going to be pulled to the right-hand side. Not all of them, but we always just draw it that way because it's easier. Leaves us with this side negative because there's more negatives than positives. This side is positive because there's more positives than negatives. What do we see? The side that's closest to the charging object are oppositely charged. They're going to attract each other. Charged objects attract neutral objects. Finally, how do you make this permanent? Notice there was not a transfer of charge taking place here. Okay? Remember that little thing, right? If there's a transfer, it's conduction. If there's not a transfer, it's induction. Okay, were they talking about clouds in the ground, or were they talking about something as fundamental as this? How do we make it permanent? We introduce this thing that we call a ground wire. And by the way, it doesn't matter where you put the ground wire. Left side, right side, top, bottom, whatever. And it doesn't, when we introduce a ground wire, it doesn't literally have to be the earth that provides the ground. Okay? Generally, it is the earth, but it could just be some other big thing that touches it and does the same thing as the ground. It could be you. You could walk over and touch something and discharge it. Okay? When you walk over and touch the light switch and get a shock, you're essentially acting as a ground. Okay? You're causing the electrons to leave to you. Okay? When you walk over and touch somebody and give them a shock, they're essentially acting as the ground to you. Okay? Usually it's a wire literally that goes into the ground, but it can be some other object that does the discharging. Okay? Bottom line is, what happens in the first case here? Well, these electrons were pushed to the left-hand side. Now they're going to keep moving to the left-hand side as far down as they can go. That leaves us with a positively charged object. Cut the ground wire, and it's positive forever. It's permanently positive. Okay, in this one, the electrons get sucked up by this positive. They get pulled up in the positive. Got a bunch of extra electrons. Cut the ground wire. Now it's permanently positive. We still call this, listen carefully, we still call this charging by induction, even though there's a transfer of charge taking place here, because this thing that's doing the charging isn't transferring. Got it? Even if there's a transfer within the process somewhere, what's important is the thing that's doing the charging. This rod that's circled in red there isn't transferring charge, so it's going to be called induction every time, even when there is that permanent charge developed here because of that ground wire. Okay? Now you look like you have a question there. No? Good? Okay, just a couple more minutes here before we get to a little bit of a break with a question to work on here, all right? We don't often see this thing with the electroscope. I showed you what an electroscope is. We didn't demonstrate it in class because I find they don't work very well. At least the ones that we have don't work very well. Bottom line is an electroscope detects charge. If you remember an electroscope, it doesn't tell us what kind of charge we have. It doesn't tell us how much charge we have. It just tells us that we have charge or that we don't have charge. And it looks something like this usually. Here we get these two leaves. Sometimes there's these two small, light pith balls on the end of a string, as opposed to these two foil leaves. Same thing happens though. You bring a negatively charged object nearby. It pushes all the negatives down into the leaves. They're like charges. The leaves spread apart. If I was to bring a positively charged object nearby, all the negatives get sucked up into the ball of the electroscope, leaving the leaves positively charged. If they're like charged, they spread apart. So if there's positive or negative charge there, they're going to spread apart. You know what happens if we were to ground this? Doesn't matter which side we ground it on. What's going to happen? We push electrons down, we suck electrons up. This is positive. I don't care what this is. This thing that's doing the charging is positive. What's going to happen? Are you going to push electrons down this way? Or are you going to suck electrons up this way? Push them down or suck it up? Yep. Going to suck it up, right? Electrons are going to go up here, and then you're going to get a bunch of extra electrons in there, and it's going to make it negatively charged. Then if you cut the ground wire, these leaves are permanently negatively charged now, right? So the leaves are going to stay spread apart. At least not forever, right? But eventually they'll discharge electrons into the air. Okay, but at least for the time being, they're going to stay spread apart, even if we take this object away. All right, good. All right, let's get into some more meaty things where we're going to deal with some math here. Just a couple minutes here. Notice at the top of this category, topic 20, electric force, we've got two physics principles listed here. Accelerated motion, work energy theorem. Typically, we'd be dealing with this accelerated motion. Why? Because if you have an electric force and it's not balanced, then it's going to accelerate, right? It's going to speed up or it's going to slow down, right? Probably speed up if it's not balanced. So probably dealing with principle number one there. The torsion balance experiment. Remember we had same thing as physics 20 almost with the torsion balance experiment for gravity. Two charges, call this Q1. Another charge we call Q2, bring it nearby. It's going to attract or repel. Doesn't matter whether it attracts or repels. We measure the value of R. We measure the value of, that's the distance that separates them, the charges. We can't, by the way, actually measure the direct value of Q1 and Q2, or at least Coulomb couldn't measure directly the values of Q1 and Q2. Rather, he measured the relative values. So let's say that charge 1, we call it Q. Okay, whatever it is, we call it Q. If we touch it against something that's neutral, it becomes a half Q. We touch it against something that's neutral again, it becomes a quarter Q, and so on and so on and so on. So we can manipulate the charge. We don't know exactly what the charge is in coulombs, but that doesn't really matter, because in the end, we know what the charge is relative to what it was. So that's how he manipulates charge. He measures the value of F, by the way, by how much the string twists, the angle of twist, the angle of deflection of it. There's a whole bunch of experiments here. First one manipulates the value of Q1, responding as force, gets a graph that looks like this. Second one manipulates the value of Q2, force, gets this one. Third one manipulates the value of R, gets a graph that looks like this. So this one tells them that force is related to Q1, force is related to Q2, force is related to, this one's kind of weird, right? You get a shape that looks like this, it's 1 over R squared. Puts them together, oh, F is going to be related to Q1, Q2 over R squared. And that little proportionality thing just gets replaced with a constant. K, Q1, Q2 over R squared. So there's Coulomb's law. Yeah, I got a question for you, just as a little aside here. If I took this graph, F versus R, right there, I can't deal with that right now, right? I don't know how to deal with that right now. All the graphs that I can deal with are straight line graphs. So I can use y equals mx plus b, right? How could I turn this into a straight line graph so that I could deal with it? Any idea how I could turn F versus R into a straight line graph so that I could deal with it the way that I always deal with straight line graphs? I'd have to replot it. And I'll tell you, on your diploma exam, you're not going to have to replot a graph, right? But maybe they ask you, what would you have to replot? What graph would I have to plot in order to make this graph a straight line? Yeah, good. F versus 1 over R squared. Then it becomes a straight line, and then I could use my whole y equals mx plus b thing in order to do my thing, right? I'd be surprised if you have to do something like that. You certainly won't have to replot it on a multiple choice exam. Does that make sense where that comes from? Look, if we know the relationship is F is equal to something over R squared, then let's plot F versus something over R squared. And then that's going to give us a straight line. Take a look here. Y equals mx plus b. F is equal to the slope times 1 over R squared. That's looking a lot like F is equal to KQ1, Q2 over R squared, right? All right. The inverse square relationship, same as gravity, right? The inverse square relationship just tells us that it's inversely proportional to the distance squared. Every once in a while, we see a multiple choice question that asks us to compare gravity against the electric force. And one of the things that they compare is the relationship. It's the same relationship. F is related to the inverse of the square of the distance. Another thing that they ask us to compare sometimes is the size of the force. You guys remember which force is bigger? Gravity or the electric force? Almost always. One of them is bigger than the other, and a lot bigger than the other one. Look at the constant here. G m1 m2 over R squared for gravity. K Q1 Q2 over R squared for electric force. This value was 6.67 times 10 to the minus 11. This value was 8.99 times 10 to the 9. Tell me now which force is a bigger force. All other things being equal, this is going to be a way bigger force, right? 10 to the 20 times bigger, because that constant is so much bigger. Okay, the electric force is the same relationship as the force of gravity, inverse square relationship. Electric force, however, can be attractive or repulsive, unlike gravity that's always just attractive. But the magnitude of the force, not even close. The electric force is almost always bigger because of that constant at 10 to the 20 times bigger. As far as the equation goes, we just wrote it down, right? KQ1, Q2 over R squared. Probably the hardest one to rearrange for would be R. Take it up by multiplying. Take the F down by dividing now. How would you find R now? What's the last thing you do to find R? It's the easy step now, right, Jonathan? Yeah, you square root both sides. So it becomes the square root of KQ1, Q2 over R squared. Over F, I should say. I'm not going to go through the solving for Q1 or Q2, but in the end, make sure you can do that. Okay, make sure you can do that. Probably won't have to, but just in case, okay? Now, one final thing with that before we move on there. I've seen a question a couple of times where they talk about identical charges and you have to find the value of that charge. If that's the case, if you want to find Q, when these are identical charges, here's what you do. You set Q1 and Q2 equal to the same thing, K times Q, which becomes Q squared. And then you solve for Q. Okay, this only works if the charges are the same value, right? If they're not the same value, then you'd have to have the value of one of them. And of course, it's a force. There's a direction associated with it, right? Now the equation is going to tell me what the direction is. It only gets me the magnitude, but I can figure out what the direction is, right? If they're like charges, it's a repulsive force. If they're unlike charges, it's an attractive force. And I can figure out whether the force is left or right based on whether it's attractive or repulsive. All right, we're going to take a little bit of a break right now. I'm going to have you work on a multiple choice question. It's going to be multiple choice question number 3 in the booklet that I photocopied for you, please. All right, what's the other topic that goes with this besides Coulomb's law? If you look at the physics 30 and 16 pages, it would be topic number 7, right? Variable value changing. The reason that I've listed that as a separate topic is not because so much it's an objective in physics 30, but because we have to do it with all kinds of different equations, including Coulomb's law. Coulomb's law is probably the most common place we see it because of that R squared thing on the bottom. They like to trip you up with that R squared on the bottom here, okay? Let's see if they trip you up this time. It says one charged object exerts a force on the second charged object. The distance between them is doubled. The charge of one of the objects is doubled, then the electric force that one charge exerts on the other is what? Well, what we got to do is either find an equation that's relevant or derive an equation that's relevant. This one, it's just find one. We're going to use F is equal to KQ1 Q2 over R squared. This is what I'm going to call my original force. This is what I start with. Okay, this is what the force is before I do anything to it. Now, my new force, this is after I make my changes, is still the constant times the charge divided by the distance squared, but we're now going to call the charge and the distance by a different symbol. Okay. What are we doing here? We're doubling one of the charges. So it's going to be, instead of Q1, we're going to call it 2Q1 because we're doubling it. The other one is staying the same. And we're doubling the distance. So it's going to be 2R. What do you got to be careful of here? What's the big thing you got to be careful of here? And the reason they like to do this with Coulomb's law as opposed to some other equations. Put your brackets around the 2R. We're not squaring R. We're squaring the distance that separates the two charges. Okay, that means we're squaring 2R, which becomes, pull the numbers out front here, 2KQ1 Q2 over, now 2 squared is 4. So over 4R squared. In other words, it becomes a half of what it originally was, a half of the old force or the original force. So the answer would be B. How many people got that? Good, good. All right. Just remember, you know what, actually, we'll move on here. So finding the force, right, we didn't do a calculation involving the force. We did a variable value changing. But if you can do that, then you can use the equation to find the value of the force. If you want to find the acceleration, get the force. Listen, if you want to find the acceleration, the force needs to be with you. Okay, may the force be with you. If the force is with you, then you can get the acceleration. Then you can get the acceleration easily by saying A is equal to F over M. That applies to this situation, but anything else as well. If you want to find an acceleration in physics 30, get the force. Okay, the force needs to be with you. And then you just use A is equal to F over M to find the acceleration. What does this mean? Touch, then force. They like to throw questions like this at us too. When you got two charges, maybe it's, you know, plus 5 coulombs and plus 7 coulombs. We touch them together, and then we want to find the force. Make sure you make them both 6 coulombs. We talked about that earlier, right? You touch two things together, they balance, and then you've got to do something else. Don't say K times 5 times 7. It's K times 6 times 6, which you might not think gives you a different answer, but it does if you look at it a little bit closer. Balancing electric force with gravity, right? Remember we seen that word suspend, hover, balance, anything like that. Something, some force has got to be equal to the gravitational force. In this context, okay, it would be the electric force is equal to gravity. But it could be a magnetic force equal to gravity as well, right? If it's a magnetic field. Look at the field. If it's an electric field and it's hovering or suspended or whatever, then it's electric force equals gravitational force. If it's a magnetic field, then it's magnetic force equals gravitational force. Solve problems like this. Okay, we want to find the net force on the middle one here. Well, we'd say draw a free body diagram, right? There's a force upwards caused by this one. There's a force to the right caused by this one. Get the force there. And then redraw it as a vector diagram. What do you do with this? What do you do with this now? You get that right angle triangle vector diagram. In physics 20, we said that's the goal. You want a right angle triangle vector diagram. What do you do with that? It's grade 9 math now, right? What do you do with that? Pythagorean theorem, yeah, Pythagorean theorem. F is equal to a squared plus b squared, or x squared plus y squared square rooted. Okay? And theta is found by the inverse tan function of opposite over adjacent. If you got a funny angle, I'd be surprised if you got a question like this with 3 charges involving a funny angle, but What would you do if you did? Instead of having this diagram right here where you're trying to solve for the force on the middle charge there, maybe you got something like this, where you're trying to find the force on this one. Well, there's a force downwards caused by this one. There's a force upwards and to the right caused by this one. You need to have this angle right there. You'd resolve this angle right there into an X and a Y components, right? We don't like funny angles. What do? We get rid of them, turn it into an X and a Y. So basically, this thing right here would become, it would turn into an X component and a Y component. Then what do? Combine the X's, combine the Y's, and draw this diagram. I don't think you're going to see one like that. Okay? I think there's a very good chance you'll see one like this. I think there's a very good chance. Okay? But I'm pretty sure you're not going to see one like this. You never know. So just want to expose you to it just in case, Okay? Deal with the funny angle because we don't like funny angles. Get an X, get a Y, replace it, and do your thing. Okay, I got another question for you to work on. It's going to be something like this, though, as opposed to something like this. I'm going to ask you to take a quick look at number 21. We're scrolling way down to multiple choice number 21 now. Second to last question on the booklet here. All right, in this question we got 3 charges. One of the things that we want to notice right away is this whole microcoulombs thing. Okay, pay attention to that, right? This is a numerical response question. If you don't convert that to coulombs, and we convert that by multiplying it by 10 to the minus 6, then you're going to get the wrong exponent. And you can do everything right with the wrong exponent and get a 0 to 1 for this. Okay, you get a 0%, no part marks in these things. Okay, we also got directions down here. This is kind of a little bit wacky. The last couple of years, they've started putting questions on there like this, and we've seen a couple of those questions. We just don't have a whole lot of them to give you as practice questions because it's a fairly recent thing that they've started doing on diploma exams. Okay, it's a way for us. It's a way for them to ask you what the direction is without asking you to calculate the angle involved. Okay, let's get the magnitude of the net electrostatic force first here, okay, because that's the first thing we want here. A, B, and C, so we want the exponent there as well. Okay, let's first draw a free body diagram on charge, I think it was on charge 2. Yes, on Q2. Notice it's the middle one, right? Okay, it's not likely to be the first one or the third one because then we'd have to deal with the funny angle thing, which means more work here. We know that these two are opposite charges. 2 is going to be attracted towards number 1. We'll call that F12. 3 and 2 are opposite charges. 3 is going to be pulled, 2 is going to be pulled down towards number 3 there. What happens to number 1 and number 3? Yeah, they're pulled to the right and up, but that's not the question. We care about what happens to number 2. Pulled to the left as a result of that attractive force, pulled downward as a result of that one. Okay, let's get both of those forces. I'm not going to go through that process right now of finding both of those forces. I'm going to trust that you guys can do the math there, making sure that you use microcoulombs. Who's got a value of F12 there? You agree with that? 0.03596. If you forgot to convert microcoulombs to coulombs, you're going to get the same number, but you're going to get a different exponent, right? So it's going to be, decimal place is going to be shifted over. What's the value of F32 there? Same thing? Oh, that makes sense, yeah, because it's the same distances and the same charges. So give me a break there, right? 0.03596 newtons. And then if we want to find the net force, we're just going to do this, okay? 0.03596, 0.03596, do the Pythagorean theorem. And what does that work out to be? .0508, we agree? All right, so we're going to express that now in scientific notation. 5.1 times 10 to the minus 2. So we'd express our first 3 digits, A, B, and C, as 5, 1, 5, 1, 2. Now, E is the direction. What's the direction? We have it drawn down and to the left. So the answer is going to be 7, right? direction 7, which is down into the left. 5127 is our answer. Good. Okay, I got another one for you here, guys, and we're going to go through this one together, okay? This one's a nasty one. It's not the one that I was talking about early on, but it's a pretty nasty one here. So it says a charged sphere. This is number 17, by the way, 17 and 18. A charged sphere that has a mass of 3.5 times 10 to the minus 4 kilograms is suspended on an insulated thread between two vertically oppositely charged parallel plates. Plates are 0.15 meters apart. There's an electric field there of 6.57 volts per meter. A charged sphere comes to rest such that the angle of deflection is 8 degrees. And the distance from the sphere to the positively charged plate is 4.0 times 10 negative 2 meters. And we have an incomplete free body diagram. All right. So what's going on here? We have an electric field that goes this way from positive to negative. We'll talk about electric fields in a few minutes here. And we know that that sphere must experience an electric force this way. Otherwise, it wouldn't move to the left, right? So there's an electric force to the left there. What kind of charge does it have to be? This goes to something that we're going to talk about in a couple minutes, but it's not the thrust of the question. You guys can answer it for me right now, though. If it's an electric force opposite to the field, it's positive or negative, Hugh? Good, it's a negative charge. I don't know if that's going to matter to me, but hey, we also have a force of gravity acting down, right? In fact, look, they have a force acting up this way, which is tension. There you go. There's 3 forces acting here. There's an electric force to the left, there's gravity acting down, and there's a tension that's acting up and to the right that counters gravity and the electric force. And here's the big thing, guys. It says it comes to rest. Somewhere here it says comes to rest. So what do we know if it comes to rest? Forces must, what's the word I'm looking for? If it's at rest, the forces must balance. Forces got to balance. So that means if we redraw this, that means the x component of tension has to be equal to the electric force. And the y component of the tension, let's do it over here actually. The x component of tension has to be equal to the electric force, and the y component of tension has to be equal to the force of gravity. They have to balance. The upward force has to balance the downward force, and the right force has to balance the left force. So it's really the blue forces that are the real forces. I've got them drawn in green here as the balancing forces. This green FG is really not force of gravity, but rather it's the y component of the tension. Okay, and the FE green one here is the x component of tension. It's not really the electric force, it's the force that balances the electric force. All right, so what they're asking me here. These diagrams showing direction again. What are they asking me in this question? What's the direction of the force of gravity acting on the sphere? All right, that's going to be downwards, right? So gravity is going to be this one. They're asking me for the direction of the electric force. Well, we know that's going to be to the left because we already have that drawn to the left. So that's going to be the electric force. And we're looking for the force acting on the charged sphere that has the largest magnitude. Oh, that's a good one. Which one's the biggest? FE, FG, or FT? The tension is gravity and the electric force combined. That's got to be the biggest force, right? You can't have force A and force B, combine them, and get a smaller force than A and B. The biggest one has to be the hypotenuse, right? And the hypotenuse is the tension there. So my force of tension is my biggest one. So my answer is going to be 6, 4, 3 for that question. We'd express that 4 blanks here. We'd express it in the first 3. Never leave that first blank blank, or that first box blank. Oh, number 18, the magnitude of the charge on the sphere. Oh, this is the ugly part right here, the magnitude of the charge on the sphere. What's the charge? Ooh, how do we even tackle this? Look, we know this angle is 8 degrees, right? We know what gravity is. Gravity is it's this downward force, but it's equivalent to the adjacent side of this angle. Right? It's equivalent to the y component of tension. It's m times g. Okay, we can find the value of the electric force that way. We can say tan 8 degrees is equal to the opposite, which is the electric force, over the adjacent side, which is gravity. Okay, using the green triangle there. So the electric force is equal to mg tan 8 degrees. Right? Then what? Well, then what? We want to say the electric force is Q times E. Sorry, we want to say it's KQ1, Q2 over R squared. But we've only got one charge here. So let's set it equal to Q times E. The electric force is equal to Q times the electric field. And we solve for Q there. We've got the electric field, we've got the mass, G, and we've got the angle. We can solve for charge. That's a hard question. Yeah, that's a hard question. This is as much vector analysis as it is physics 30, but it is what it is. All right, guys, let's take a look at topic 21, which, again, you can see that the physics principles would be accelerated motion or work energy theorem, most likely accelerated motion there. Okay. Electric field, sometimes we define it as a sphere of influence or a line of influence that surrounds an object with charge, but we can also define it as this region in which an electric force could be experienced. A region in which an electric force could be experienced if there was something there to experience it. The direction of the electric field, this is important. This is so important here. The direction of the electric field we define in one of 2 ways. Okay, it's away from positive, and corresponding to that, it would be toward negative. But here's the big thing right here. We define it as the direction that a positive charge moves. Let's say the direction of the force on a positive charge. The direction of the electric force on a positive charge when the positive charge is exposed to that field. So that means that if you have an electric field to the right, that means a positive charge must move to the right. But if you have an electric field to the right, that means a negative charge would go opposite to that. Positive charge with the field, negative charges against the field. How many times have we seen in the last little while when we're talking about Millikan's oil drop experiment, needing to be aware of that, right? Needing to remember that positive charges experience the force with the field, negative opposite to the field. Don't get that mixed up with the hand rules, right? Hand rules are for magnetic fields, and we'll talk about those shortly. Okay, this is just always a force in the direction of the field or opposite to the field. Now, sometimes we see a situation like this, right? Here's an electric field. Here's a positive particle moving through that electric field. What happens to it? Well, it experiences a force downward in the direction of the field, but that doesn't mean it's going to move downward, right? Just like when I throw a ball, it experiences a force of gravity down. It doesn't move downward. It follows a parabola, right? Well, that's what's going to happen with this as well. It experiences a downward force, which means it's going to curve downwards. That's a parabola as opposed to a circle. Okay, if I had a real similar situation, but this time it was an electric field downwards and a negative particle moving to the right, then this time it would experience a force upwards and it would go like this. It would be a parabola upwards. It would be like projectile motion in reverse. Projectile motion in the bizarro world, where Gravity is acting up. Okay, it's a parabola, but a curving upwards parabola. Okay, be aware of the field diagrams. Okay, the field surrounding positives and negatives, the field surrounding charges, okay, when they're nearby each other. Okay, the field surrounding like charges, right? They don't join up like this, right? And remember that when field lines join, right? When field lines join up, we got something like this. That's an attractive force. When they don't join up, we have something like this, a repulsive force. So again, just remember, they join up. It's attractive, no matter what the diagram looks like. They don't join up. It's a repulsive force. Again, regardless of what the diagram looks like. Sometimes it's as simple as one that we've done in class. Sometimes it's a more complicated diagram. Okay, look for the field lines joining up or not if you want to determine whether they attract or repel. Okay, we talked about these already, E and F. We got three equations here, and it kind of goes along with G, H, and I. Three equations that we have here. We have the producer equation. We have the experiencer equation. And we have the parallel plate equation. And remember we drew in class that Venn diagram? Isn't that what a Venn diagram is? The thing that's in the middle, whatever is in both of the circles, fit into both categories, right? So the top circle is showing us essentially what equations we can have in a what equations we can use in a non-uniform field. This is a producer equation when we have a single point charge. This is an experiencer equation when we know something about what feels the field, but we can use it when we have a non-uniform field. The bottom one is the parallel plate equation. It's valid when we have a uniform field. Okay, what do we know about the middle equation? It's valid anytime, whether it's a uniform field or a non-uniform field, as long as we know what the force is that's experienced by the charge. A lot of times, by the way, okay, you've seen this a lot, that we have to actually use this equation for force here, given the electric field. Okay, we did that in a question that we just did a few minutes ago. So if KQ1, Q2 over R squared, it's Q times the electric field to find the value of the force. Usually that happens if you don't have the values of two charges. You got one charge, you want to find the electric force, use that equation. If you've got two charges, use Coulomb's law, usually. Got to erase some stuff here. It's getting a little cluttered here. The graphs. Well, we say a graph representing the field force caused by a point source, parallel plates, and so on. If we had this graph for the first equation, what would it look like? Tell me what it would look like. Straight line, curved line, upwards, downwards. KQ over R squared looks like this, right? F over Q. Oops. Say it's the relationship between E and F. As F goes up, E goes up. It's a linear relationship, right? Oh, here's a good one here. How about the electric field as a function of the distance between the plates? It's going to curve downwards as well. Even though it's not D squared, it looks almost the same as this one. Okay, these two look almost the same. Okay, E related to the inverse of R squared, E related to the inverse of D. Even though it's not D squared, it looks almost the same. Okay, just sketching it would be indistinguishable. All right. What about this one, though? What about, let's call not delta D, let's call it D, the distance from one of the plates. So here's a charge. D isn't the distance between the plates, it's the distance from one of the plates. What if I plotted a graph of E versus D? What would that look like? I love this question. Why would it look like that? Why would it be a straight, flat, horizontal line? Go ahead. Good. Where the particle is has no bearing on what the field strength is going to be. All right? Got it? So the distance between the plates matters. The distance from one of the plates doesn't matter. All right. Let's take a look at these ones here. Similar to charges, right? Similar to electric forces here. I got a charge right here and a charge right here, and I want to find the field strength right here. There's a field to the right caused by the first one, a field to the right caused by the second one, away from the positive, toward the negative, two different fields. Okay, get both of those using KQ over R squared, and then add them up, both to the right, so both positive. If it's two-dimensional, I'd be surprised if it's two-dimensional, something like this, but I suppose you could. There's a field toward the negative. There's a field away from the positive. Get the value of both of those fields, and then what would you do with them? Pythagorean theorem, right? And the inverse tan function if you had to find the angle. And finally, here's two parallel plates. Here's a positive plate. This goes with topic P here. Here's a negative plate. There's an electric field going from positive to negative, right? Always goes away from the positive, always goes toward the negative. I'm going to give you a couple different scenarios here, and I want you to tell me in which scenarios is work done. In which scenarios is work done? Okay. I'm going to move a charge, a positive charge, this way. I'm going to push it this way toward the positive plate. Do I have to do work to do that? Yes. I have to use energy to do that, right? Because it doesn't want to go towards the positive plate because it repels it, right? I have to do work to do that. What if I push it this way? What if it's moving to the right? Is there any work done on it when it's moving to the right? No. No. Why not? Work is F times D. And what do we say about F and D? They have to be in the same direction. Okay, the electric force on this positive particle, they have to be parallel to each other. The electric force is downwards. Okay, that's parallel to this one. So work is done when it's parallel. If the electric force on this one is downwards, then that force and that displacement aren't parallel. So there would be no work done on that one. There would be work done on this one. Because the force is parallel to the displacement. I got 3 questions that I want to work on here. Actually, I got 4. I'm going to start off with questions 6 and 7 in the booklet that I photocopied for you, please. All right, the question says a negatively charged glass bead is released from a location directly above 2 vertical oppositely charged plates near the Earth's surface, enters the region between the plates as shown below. Hey, first of all, regardless of the plates, can you tell me why this thing falls? This is not meant to be a hard question. Why does this glass bead fall? Because of gravity, right? It falls because of gravity. We know there's a force of gravity acting down on it. We also know there's an electric field. The electric field goes from positive to negative. So there's a gravitational field downwards. There's an electric field to the left. Now, what's the question? 6 says the direction of the electric force experienced by the charged glass bead is which way? Well, it's a negatively charged glass bead. Negatively charged glass bead. Okay, if we have a field to the left, a negative experiences a force to the right. So the answer is towards the right side of the page for the electric force. Good? And question 7 says, which of the following rows matches the type of motion exhibited by the glass bead as it travels through the region between parallel plates with the direction of that motion? Remember I said when we were going over those physics principle problems that we know we're going to get 2 questions that go together, physics principles, but we often now get physics principles listed in other questions as well. This is one of those other questions. So the horizontal motion, left or right, what kind of motion would it be? Would it be uniform motion or accelerated motion? In other words, is it going at a constant speed horizontally or is it accelerating horizontally? Who said constant speed? Who said accelerating horizontally? Okay, yeah, it's accelerating horizontally, and we know that because there's an electric force. If there's a force, there's an acceleration. So it's going to be either A or B. What about vertically, up or down? Well, it's gravity. Gravity causes it to accelerate. So it's going to be uniformly accelerated motion in both cases. The answer is going to be B. Okay, take a look at question number 4 now. Okay, let's have a look, guys. Number 4 says, which of the following graphs best shows the relationship between the electric field strength and the distance from the source charge? The source charge, we're talking about a non-uniform field, so we're talking about the producer equation here. You ever want to find a graph that shows a relationship? Get the relationship. Get the equation. Okay, we're looking for the relationship between E and R. Okay, that is not a straight line graph. Okay, E and Q would be a straight line graph. E and R would not be a straight line graph. In fact, if I was to plot E versus R, it would look like this, right? Because it's an inverse relationship. They got all 4 straight lines here. How would I straighten this? How would I make that a straight line? Which graph would I have to plot to make that graph a straight line? A, C, or D? Which one is it? Who said A? Who said C? C is the correct answer, right? How do we get that? Because we know that it's something over R squared, so we're going to plot something over R squared to get the straight line. Okay, one more before I do some more stuff here. This is number 15 that I'd like you to do right now. Everyone take a look up here. The question says, look, we get 2 parallel plates. We got a distance between the plates, a potential difference between the plates, and then we have 2 locations, location 1 and location 2. We want to know the work that's required to move an electron from location 1 to location 2. So it starts here and it ends up right here. Okay, work is equal to F times D. On your data sheet, it actually says F times D times cosine theta, but normally we can ignore that cosine theta. If it's moving parallel to the force, then theta is 0, which means cos 0 is 1, which means the equation becomes F times D. In physics 30, if you're going to have to use this equation, it's almost a guarantee that you're going to be able to drop the cosine theta, and you just leave it as F times D. All right. What's the force here? We don't know. Okay, we can find it, though, because we know the field. This is a tricky question. We know the field is delta V over delta D, which is 1,200 divided by 0.20, not 0.16. Okay, the field is dependent upon the distance between the plates. Okay, 1,200 divided by 0.2, I think is going to give me 6,000 volts per meter or newtons per coulomb. Okay, and then we can say that force is equal to Q times E. This comes from the experiencer equation, right? What's the charge here? It's an electron, so it's 1.6 times 10 to the minus 19 times 6,000. What's that equal? 9.6 times 10 to the negative 16. There's my force. All right, let's multiply my force. times what? What are we going to do? The hypotenuse of this? Is that right? No. What distance do we use? Just the 0.16. Okay, remember, what did we say a few minutes ago? To go this way in a field that's this way, there's no work. Right? It's got to be parallel. Okay, so this 0.06 is completely irrelevant. Completely irrelevant. They're just throwing that in there to mess you up. And I guarantee you, if you do the hypotenuse there, I don't know which one it works out to be, but if you do the hypotenuse, one of those answers is going to be the hypotenuse, based on the hypotenuse. Okay, use the displacement that's parallel to the force. If the force is downwards, then use the displacement downwards. I don't care about the horizontal displacement. We're not going to spend very much time on topic 22 at all. Just to remind you that if you have a uniform surface, doesn't matter what the shape of it is, if it's a uniform surface, the charges will be evenly distributed on the outer surface. So whether it's a plate, or whether it's a solid conducting sphere, or whether it's a hollow conducting sphere, the excess charges, not all the charges, but the extra charge, go to the outside, the outer surface, and they're going to be evenly distributed. If you have a pointy thing, which is a non-uniform shape, they're still going to be on the outer surface, but this time they're going to be more concentrated at the point. They always go to the outer surface. They're evenly distributed if it's a uniform surface, but it's a higher concentration of charge at sharper things or pointy things. And a Faraday cage is just the idea that the net electric field inside a conductor is zero. And that's why it's safe to be inside your car in a lightning storm. Right? In fact, it's one of the safest places to be because your car is a conductor. And even if the lightning strikes your car, the net electric field inside that conductor has to be zero. And if there's no electric field, it can't affect you, can't hurt you. Okay, we went through a lot more detail than that when we did it in class the first time. But if you remember the gist of it, like what I just wrote down there, you're going to be just fine for that. And finally, conservation of energy. We talk about a car going down a hill, or talk about a car going up a hill. Basically, we say when a charged particle speeds up, it's like a car going down the hill. And when a charged particle slows down, it's like a car going up the hill. And we treat it as a conservation of energy problem in both cases. But this time our energies are not gravitational potential and kinetic, but rather we're dealing with electric potential and kinetic. So in this case, we'd start off with potential, we'd end up with kinetic. In this case, because it's moving, we'd start off with kinetic, and we'd end up with potential. You may also have kinetic up here if it's already moving, and you may have kinetic up here as well if it's moving at the top of the hill, if it hasn't just barely reached the top of the hill and come to a stop. So let's describe the conversions of energy that are taking place there. Okay, in the first case here, if we start off with a speed and a potential, right, we're at the top of the hill or we're accelerating the charge across the potential difference, then we start off with potential and kinetic, we end up with kinetic. It's a conversion of potential to kinetic. If we're going up the hill or slowing down, it's a conversion of kinetic to potential. If you gain speed, it's a conversion to kinetic. If you lose speed, it's a conversion from kinetic. So be able to describe those conversions as well. And finally, be able to calculate charges speeding up and slowing down using EI equals EF. QV plus 1/2 mv squared equals 1/2 mv squared, or whatever the case may be. There's a couple questions I want to do on that here. I'm going to go through those as quickly as possible so we can finish up our magnetism stuff as well. What I want you to look at right now is on your electricity and magnetism question number 8. The question talks about an electron here going into this gap between two parallel plates. We know that there's an electric field to the left, away from positive toward the negative. It's a negative charge. So as a negative charge goes into that electric field, it will experience a force this way. If it experiences a force this way, it's going to accelerate. That's like a charged particle. A charged particle speeding up is like a car going down the hill. The question here in number 8 asks us for the energy conversion, first of all, that takes place. Okay, basically, what happens to the potential energy? Well, as this car goes down the hill, as it speeds up, what happens to its potential energy? It decreases, right? Its kinetic increases, its potential decreases. So we're going to say that the answer either has to be A or B. The potential energy decreases. Car speeds up as it goes down the hill, kinetic increases, potential decreases. Charged particle speeds up, kinetic increases, potential decreases. All right, what about the force? Oh, that's a good question. What about the force? How is that affected as it goes across the gap? We know the force on this particle in between these plates is Q times E. And we know that E is a uniform field, right? If E isn't changing, then what happens to Fu? It doesn't change either. So the force stays the same. So the potential energy decreases, the force remains the same. Quick look at number 10. Number 10 asks us for the final energy of the electron just before it strikes the positive plate. I'm just going to show you this one just in the interest of time here. The final energy right here just before it strikes the plate, right here. Okay. It's a car going down a hill. It's a conservation of energy problem. What kind of energy does the car have at the top of the hill? Well, it's got potential and kinetic because it's already moving. It's got an initial speed. But it's not gravitational potential, is it? It's electric potential. We're not going to get rid of that kinetic, though, because it's moving when it enters this gap. Sometimes it's at rest, and this is 0. Sometimes it's moving, and it's not 0. And we're solving for VF there. Hey, we got all our numbers here. Just remember to drop the sign of the charge in there. Okay, plug everything in here, guys. We got potential difference. We've got the mass, got the initial speed. Solve for the final speed. Sorry, actually, we're not solving for the final speed. We're solving for the final energy, right? So what would we do? Instead of putting 1 half mv squared in there, we would just say EF, right? The final energy. If we're looking for final speed, we put in 1 half mv squared. Looking for the final energy, we'll just solve for EF there, which is equivalent to the initial energy. Now let's take a look at our magnetism. Some of this stuff we'll go through pretty quickly in the interest of time. Some of it we'll spend a little bit more time on here. Domain theory, remember, okay, tiny little regions inside a ferromagnetic material. Ferromagnetic material, by the way, can become magnetized. Not necessarily a magnet, but it can become magnetized. And domain theory just says that there's these tiny little regions called domains inside this ferromagnetic material, and they normally point in random directions, but if we magnetize it, then those domains are going to point in the same direction. So here we have a magnet, and here we have just a non-magnetized ferromagnetic material. And we can do that, magnetize it by bringing another magnet nearby. So look, we got a magnet that's already has its domains aligned here. These domains influence these domains to point in the same direction, or you can wrap a wire around it and apply an electric current through that wire. Poles versus charges, just to remind you that they're two different things. Talking about a north pole, it's not a positive, and a south pole is not a negative. And then, of course, the 3 magnetism laws. Like poles repel each other. Unlike poles attract each other, and both north and south attract non-magnetized ferromagnetic, kind of the equivalent of charged objects attract neutral objects. Remember that charged attract neutral because of a separation of charge, whereas a magnet attracts a non-magnet because of a temporary alignment of domains, kind of like a temporary separation of charge. such as the temporary alignment of domains. The magnetic field, again, this region in which a magnetic force could be experienced. Here it goes from north to south. That's, by the way, from north to south outside of a magnet. Which way does it go inside of a magnet? South to north, right? Yeah, it's like this. Here's your magnetic field outside from north to south, but inside it goes from south to north. We also define it as the way that our compass needle points. Compass needle points in the direction of the magnetic field, which is the same thing from north to south, but it's maybe a more concrete way of observing it. It's a vector field, has directions. Can you be able to do the field diagrams? Biggest thing with these field diagrams, again, just like with electric fields, if the field lines join up, then it's attractive. If the field lines don't join, then it's repulsive. So I can see something like this. I may not know what the poles are there, but I can determine that that's a repulsive force just by virtue of the fact that the field lines don't join up. Here's a good one right here, and a really, really important one right here. The effect of a magnetic field on positive charge, a negative charge, and a neutral charge if it's stationary and moving. Let's make a little table for this, actually. This is in a magnetic field, right? There is no force, there is no effect on a neutral charge if the charge is stationary. In fact, it doesn't matter if it's moving, there is no effect. A neutral object is not affected by a magnetic field ever, no matter what. A positive charge does not experience a force if it's not moving. A negative charge, for that matter, does not experience a force if it's not moving. So stationary charges, neutral, positive, negative, whatever, it doesn't matter how strong it is, doesn't matter what type of charge it is. If it isn't moving, there's no effect in a magnetic field. In order to be affected by a magnetic field, there has to be a charge, and it's got to be moving. We're going to find the effect on a positive charge by the hand rule for deflection. Which we're going to talk about in just a couple minutes here. And on a negative charge by the deflection rule as well. But remember that if it's a positive charge, it's the right-hand rule. And if it's a negative charge, it's a left-hand rule. We'll talk specifically about how to do that rule in a second here. What causes a magnetic field? Magnet. Causes an electric field? Charge. What causes a gravitational field? Mass. Direction, attractive or repulsive. And of course the Earth's magnetic field. The whole deal with, you guys remember, the magnetic field goes like this, which means that technically this is our south pole and this is our north pole magnetically. Now we get into the hand rule stuff. And there's 3 hand rules that we learned about. This whole idea that 1819, Oersted's discovery in 1819 that moving charges generate electricity. Sorry, that's wrong. Moving charges generate what? An electric field, right? Moving charges are electricity. They make That's wrong too. They do generate an electric field, by the way, but in this context, they generate a magnetic field. By the way, a moving charge will generate a gravitational field because it's got mass. It'll generate an electric field because it has charge, but it'll generate a magnetic field because it's moving. Here's a negative charge going into the plane of the page. Thumb, bent fingers, counterclockwise. Here's a negative charge moving to the right. Thumb, bent fingers, magnetic field would be into the page here, out of the page below, up in the front, down in the back. Remember the whole difference between right hand and left hand? Right hand is for positive particles. Left hand is for negative particles. An electron current versus conventional current. What do we mean by that? What's conventional current? We almost always use electron current, right? Almost always. What's conventional current? Okay? Yeah, it's full of positive. It's full of positives. So if you use conventional current, just make sure you use your right hand for that. If you have electron current, make sure you use your left hand. And what do we mean by working backwards? Well, maybe you see a question like this. It says, here's the direction of the magnetic field. What's the direction of the moving particle? This time it would be, instead of thumb, fingers, see which way my fingers point, it would be fingers, see which way my thumb points. So fingers, bent fingers, clockwise, thumb out of the page here. And then the coil rule. We got something like this. This is the negative side of our battery, so it means the electrons are going to go up this way, up in the back, down in the front. Going to go around clockwise here, counterclockwise, I should say. Remember what we said to do? Make your little coil, right? Take your piece of paper, wrap it up, make your little coil. This is backwards, right? Instead of thumb current, fingers field, it's fingers current, which is down in the front, right? Fingers down in the front. Okay, you're looking at the front of this. If you get confused about that, you should label it, right? Literally, in your exam room, roll up your piece of paper and label it front and back and look at the front. Okay, fingers point down in the front. My thumb points to the left, which would mean inside the coil, the magnetic field is to the left, which means this is going to be a north pole and this is going to be a south pole. You may have to work backwards, so you may be given the polarity and say, oh, okay, look, I got to stick my thumb in the direction of the polarity, which is towards the north pole. My fingers will automatically point down in the front. So instead of fingers thumb, it's going to be thumb fingers. Again, the exact opposite to the wire grasp rule. Instead of thumb current fingers field, this time it's fingers current thumb field. And then finally the deflection rule, we'll explain that and then we'll give you a little summary of all three of these rules here. The deflection rule deals with an external magnetic field. I've bolded that. I made it capital letters because that's your little hint as to when you're using the deflection rule, right? When you've got an external field. If you don't have an external field, then don't try to use the deflection rule because there's no force. You might have a charge that's causing a magnetic field, but if there's no other field, then there's no force. This time, for this one, we got thumb in the direction of the particle, fingers field, external field, palm points in the direction of the force. Thumb, fingers, palm. Right hand versus left hand. Again, positive, negative particles. And able to work backwards. It's not always thumb, fingers, which way does your palm point? Sometimes it's palm, thumb, see which way your fingers point, or palm, fingers, see which way your thumb points. I'll just summarize these here, guys. Okay, we have 3 rules. We have our wire grasp rule. We have our coil rule, and we have our deflection rule. We have our thumb, which is our thumb point in each case. We're going to run to space here. Now I'm just creating a new page for this. We have our wire grasp rule. We have our coil rule, and then we have our deflection rule. Left hand and right hand for all 3 of them. We have a certain number of variables in all these as well. There's our thumb. There's our bent fingers. There's our straight fingers. And there's our palm. Our thumb in the wire grasp rule points in the direction of the moving charge or the electric current. It does in the deflection rule as well. In the coil rule, our bent fingers point in the direction of the current or the direction of the moving charge. In the wire grasp rule, our bent fingers point in the direction of the magnetic field. The magnetic field that's caused by the moving charge. No external magnetic field here. In the coil rule, our thumb points in the direction of the magnetic field caused by the moving charge, caused by the current. In the deflection rule, we don't use bent fingers. In the deflection rule, we use straight fingers. And that's going to point in the direction of the external magnetic field. Not the field that's caused by the moving charge, but the external magnetic field. We don't use straight fingers in either of these. Nor do we use our palm in either of these. Here, our palm points in the direction of the magnetic force. So in the first rule, thumb, current, fingers bent in the direction of the field. In the second one, it's thumb in the direction of the field, fingers in the direction of the current or the moving charge. And in the third rule, it's thumb, current, fingers stretched out in the direction of the external field, and palm points in the direction of the force. We're going to take a look at 2 questions here. Questions 19 and 22. All right, this question asks me to match the direction of the field at point P in each of the diagrams as described below. So what's the direction of the electric field in this one? Direction of the electric field in this one. Direction of the magnetic field in this one. Direction of the magnetic field in this one. Somebody was asking me just a few minutes ago, what does it mean when we see a battery like this? What does it mean for the polarity of the plates? Okay, the side that's closest to the negative will be negative. The side that's closest to the positive will be positive. What's, Jackie, what's the direction of the electric field in this one? To the left, from positive to negative. So the first one is going to be number 4. Okay, let's take a look at the other electric field here. Electric field goes away from positive. So the electric field caused by this positive at point P is going to be number 1. Now magnetic field. Here's a wire that's electron flow into the page. Thumb, fingers. This is a wire grasp rule, right? Thumb, fingers. At that point, it's pointing down the page. So that's going to be number 6. Oh, and this is the good one, the coil rule here. We know the electric current is going to the left in the back, to the right in the front. Make your little coil if you have to. Okay, I've got my fingers pointing towards the right in the front. My thumb points downwards. That means the magnetic field inside the coil is pointing downwards. So that's going to be a 6 as well. So my answer would be diagram 1, 2, 3, 4. It's going to be 1, 6. No, sorry, it's 4, 6, 1, 6. Make sense? How many people got that? Okay. Some people didn't finish, I know, because I rushed you on that a little bit. Yep. Oh, wait a sec. The third one is 1 because it's away from the positive, but I did make another mistake, not that one. Okay. The third one is 1 because that's a positive producer, and the field points away from positive producers, right? So it's down and to the right. Here's number 6. This last one's the problem, though. I found the magnetic field inside the coil. Where are they asking me to find it? Outside. So it's going to be up, isn't it? So the answer for that one's going to be 5, not 6. How many people got that one? You got to good. You got to be aware of that, right? Be alert for that. Okay, I wasn't. Hey, don't be like me. Don't make that mistake like I did. Okay, let's plug away here. There was one more question I was going to do, but it's basically a repeat of finding the magnetic field at the 4th diagram there. All right, topic 29 here. Getting there. All right, now some numbers. When we get a charged particle in a magnetic field, what do? Well, first of all, everything that we're going to show you here within these topics here, subtopics here, requires the particle to be moving perpendicular to the field. The particle in the field must be perpendicular. If they're not perpendicular, then we can't do any of what I'm about to show you. If they're parallel, we can deal with that, but if they're parallel, the force is 0. So we don't need to do anything else. If they're perpendicular, the force isn't 0. We can do what we're going to do down here in the subtopics B through I. If they're not parallel or perpendicular, we can't do it. So you're not going to see a question like that. Basically, here's what it boils down to. Okay, you will see problems where we have to find the magnetic force on a moving charge. Sometimes if we see that word suspend, etc., right, then that magnetic force may need to be set equal to the gravitational force. Sometimes it may be an electric field that's balancing it. And if it's an electric field that's balancing it, then we're going to have to set the magnetic force equal to the electric force. You have to look at context there, right? If it talks about the magnetic field and the gravitational field, then it's Fm equals Fe. If it's the magnetic field and the electric field, then it's Fm equals Fe. So QVB would be equal to Q times E. And the fourth thing that you can see is when the charged particle is going through that field, there's no other fields present, and it just goes in a circle. When there's no other fields present to cause it to balance or whatever, then it just goes in a circle. So we may set Fc equal to Fm, or mv squared over r equal to QVB. So basically, I'm telling you that when you're doing a problem involving magnetic forces, it's probably going to boil down to one of these four things. Most times, it's either going to be this one or this one. But sometimes if you see that word suspend, hover, balancing, then you may have to set that magnetic force equal to some other force, depending upon what the context of the question is. Talking about electric current here only because it becomes important later on when we talk about the force on a conductor. Just remember the electric current is the movement of charge, and the equation is Q over T. So it could be coulombs per second. What's the other set of units that we use for electric current? The amps, right? Sometimes what we got to do when we're analyzing a magnetic force on a conductor, which again, same deal applies, perpendicular versus parallel. If it's parallel, the force is 0. If it's perpendicular, then we can do all of this stuff, B through H. If it's neither, then we can't do anything. If it's perpendicular, then we're going to say F is equal to ILB. Just remember that the length that we use here is the length that's in the field. Because if you got a problem where, let's say you got a 10 centimeter long wire, but only 8 centimeters is exposed to the field, then it's the 8 centimeters that we care about, not the 10. It's only the part that's in the magnetic field. In fact, it's only the part that's perpendicular to the field. So if you got 20 centimeters in the field, but only 10 centimeters is perpendicular to the field, it's the 10 you want. Sometimes we got to find electric current using Q over T. And sometimes you got to set the magnetic force equal to the gravitational force. So instead of QVB equals mg, it would be ILB equals mg. Sometimes you might have to set it equal to an electric force. ILB, you probably wouldn't have to do that actually, not on a wire. Yeah, you probably wouldn't have to do that with a conductor. So this is likely what you're going to see in the context of magnetic force on a wire. Boy, I got a good one to go over with you in just a couple minutes after we're finishing topics 32 and 33 here. 32, the generator effect, basically. Look, you got three things. Oh, sorry, you got two things. You got a conductor, and you got a magnetic field. If you move one of them, we generate an electric current. So if I've got a set of magnets and I've got a wire and I'm moving the wire perpendicular, again, it's all perpendicular, right? Perpendicular. I move the wire perpendicular to the field that's going to generate a current. If I move the magnets and keep the wire stationary, it's going to generate a current. I got a wire, I got magnets, I move one of them, I generate a current. And remember this whole idea with the lenses law? Remember that demonstration I did in class today with dropping the magnet versus dropping just a piece of steel? I can't remember who my volunteers were that I embarrassed. But bottom line is, when you've got a wire and you've got a conductor and you've got a magnetic field, and you move one of them, you will generate a current. But that current generates a magnetic field. So you've got a magnetic field that's generating a current, but there's a current that's generating a magnetic field. Now you get two magnetic fields. There's the one that you start it with, and there's the one that you just made. Those two magnetic fields, they act together to oppose the motion of whatever it is that's moving. If it's the magnet that's moving, they oppose the motion of the magnet. If it's the wire that's moving, they oppose the motion of the wire. So basically, we use, solving a Lenz's law problem, we usually end up using the coil rule, usually, in order to determine some kind of property of this Lenz's law thing. I got a question that I want to do on that, question number 16, and then I got one more question, if we have time here, that I want to do on graphing here. So flip over to number 16 here. Let's see what you can do with this one, please. Magnet moves into a coil of wires shown below. As a result of this motion, the current is induced in the coil and a magnetic field is produced. All right, so we just said that, right? We've got a magnetic field. This is B1, the original magnetic field. That generates a current, which generates another magnetic field, B2. We just want to know what that B2 looks like here, okay? Well, we know that has to oppose it. So if it opposes it, then this must be a north pole and this must be a south pole, which means the magnetic field inside the coil, inside, goes from south to north. We want to find the direction of the electron flow. We're going to use our coil rule. Right now that we know the polarity, we're going to use our coil rule. We know that the magnetic field goes upwards inside the coil. So we're going to stick our thumb upwards. That means in the front, my fingers point towards the left. If my fingers point towards the left, then that means the current is going to go like this. So what's my answer here? Looks like it's going to be either C or D, because they both have current going towards the left. My magnetic field is going to go around like this, up inside, down outside. So it looks like the answer is going to be C for that one. How many people did C? Good. Now I got one more that I want to at least get a start on here. This is a nasty one. This is right up there with the most difficult questions that I have ever seen on a Physics 30 diploma exam. This is an ugly question. I told you, when you get that graphing question, you can deal with it. And I believe that 9.5 times out of 10, you're going to get a question that you can deal with quite easily. You get a question like this, a 0.5 times out of 10, you can deal with it, but it is ugly. Look at what they're doing here. Let me just explain it, and I'll go through with you, because honestly, you're not going to solve this on your own right now in the next 2 minutes. We've got this experimental apparatus where we've got, if you look at the first picture here, you've got a suspended conducting rod, kind of like a wire, right, in a magnetic field. And they're giving us a side view of it here right now. So this wire is going like this, right, perpendicular to the page. Does that make sense? You're looking at a cross section of it, right, of the wire. So it's not just a ball, it's a cross section of that wire. And you know that there's a current going through it, and that current, along with the external magnetic field, which goes this way, causes a magnetic force. And that magnetic force, the magnetic force on the wire is this way. So let me just draw it over here. There's a magnetic force on the wire that's this way. But there's a gravitational force on the wire that's this way. And there's a tension on the wire that's this way. Right? Here's the tension up there. So there's my three forces. I've just drawn it a little bit differently there. This is similar to one of the questions that we've done already today, right? Except it's a magnetic force. Instead of the electric force, that's the easy part. We know this angle, by the way. Well, we don't know the angle, but we know we've got it labeled as theta. And then what do they give us? Oh my goodness. They give us a graph of tan theta as a function of current. Tan theta as a function of current. Wow. What are we asked to solve for here? If we flip the page, we're asked to solve for the magnetic field. Here's your graph. What's the magnetic field? Wow. Tan theta as a function of current. What's the magnetic field? I got to be honest with you. If I was in grade 12 right now and I saw this question on an exam, I would be like, what? I would not get that question. If I was in grade 12, I would not get that question. The good news is some of you guys are smarter than I was in grade 12. Some of you guys can get this question. It's tough, really tough. One of the hardest questions I've seen ever. But we're going to go through it with you. Okay, we're going to show you that really it boils down to those graphing skills that we learned, even though it's really, really tough. Okay, so what do we got here? Well, we start off with y equals mx plus b, right? We always start off with that. If it's a straight line, y-axis is tan theta equals the slope times the x-axis, which is the current. That's the letter I, and it looks like there is no y-intercept, or at least it's pretty darn close to 0. All right, so we're looking for an equation here that has tan theta and current in it. I don't know about you, but I can't think of one off the top of my head, nor can I find one on my data sheet off the top of my head. So we have to figure out one. We have to derive one. If you guys get a question like this, I would be so bitter if I was you. Like, I'd be so mad, but you can get it. I'd just be mad, bitter, angry. Okay, so we need a tan theta. Here's the thing, guys. Just like with that electric force problem, remember we said that the y component of this tension has to be equal to gravity because it has to balance the downward force, and the x component has to balance the magnetic force, right? Except it was electric force in that other problem. Right? The forces have to balance. The upward force has to balance the downward force. The left force has to balance the right force. Now, take a look at this. Bear with me for a second. If we say tan theta, because we need a tan theta, right? So let's do something with tan. Tan theta is equal to the magnetic force over gravity. Oh, wait a second. This might actually work out. Tan theta is equal to the magnetic force over gravity, but the magnetic force is ILB, right? Over m times g. Oh, look. Tan theta disappears. I disappears. What are we left with? The slope is equal to LB over m times g. And presumably, you're going to calculate the slope from the graph with your calculator. Okay, the length of it you got, m you've got, g you've got, and you can solve for what you're looking for with the magnetic field there. It's not so much this that's the problem that makes this tough. It's combining this graph analysis with this. Okay, even as the teacher, when I looked at this question the first time, I'm like, where is tan theta coming from? But the difference between you and me, when I see a question like this, I'm going to look at it and say, where does that come from? Hey, I'm not afraid of it. Okay, I'm confident that when I do something, I'll be able to figure something out, okay? Try things, and some of you guys are going to figure it out too.